It's a pleasure to introduce Professor Casey Blacker from the US. He will speak on a Cartan theorem for simplicial Lie groups.
Great.
Please.
Thank you very much for the invitation to speak, and thank you to everyone in the audience for your attention. The structure of this talk is as follows. First, I will review the theorem of Cartan, which we seek to generalize to the higher setting. Second, I will describe that higher setting. So I'll introduce the higher setting of simplicial Lie groups and L-infinity algebras. I'm not assuming that anyone watching has a background in this. Following that, I will describe the construction of the Chevalier-Eilenberg algebra of an L-infinity algebra. And then finally, I will explain some of the recent ongoing work with my collaborators, Ethan Cleland and Michael Merkel, who are both PhD students at George Mason University. All right, so Cartan's theorem for Lie groups. We begin with the definition. Recall that the Chevalier-Eilenberg algebra of a Lie algebra G is the commutative differential graded algebra, or CDGA, with underlying commutative graded algebra given by the exterior algebra of the dual of the Lie algebra. And when I say, and throughout this entire talk, whenever I say commutative, it always means graded commutative. So actually, it's more like anti-commutative, actually. And the Chevalier-Eilenberg differential is determined by the dual of the Lie bracket. So that's kind of an unusual construction when we see it for the first time. This just means that if alpha is a dual Lie algebra element, then its Chevalier-Eilenberg differential evaluated on two Lie algebra elements x and y is just alpha evaluated on the Lie bracket of x and y. And so this this extends to a derivation on the exterior algebra of the dual of G. So in, I believe, 1929, so this is quite an old theorem, Cartan observed that there is a canonical isomorphism between this algebraic construction of the Chevalier-Eilenberg algebra and the geometric space of left invariant differential forms equipped with the de Rham differential on any Lie group to which the original Lie algebra is tangent. The idea of proof is actually quite straightforward. First, observe that the two underlying algebras are easily seen to be isomorphic, as they're both manifestly isomorphic as algebras to the exterior algebra of the fiber of the cotangent bundle of G at the Lie group identity. Second, and more interestingly, it can be seen that the two differentials correspond to each other using basic Cartan calculus, together with the observation that whenever you pair a left invariant one form with a left invariant vector field, you get a constant function on the Lie group G, so that its exterior derivative and any Lie derivative is just going to be 0. So in that manner, we can show that very quickly in one slide that yes, indeed, it seems plausible that these two things would be equal to each other. So this is interesting because it compares, it equates an algebraic construction with a geometric or analytic construction on the exponentiating manifold. Okay, so our goal is to extend this result to a higher Lie theoretic setting. Specifically, we want to replace the Lie groups with simplicial Lie groups and the Lie algebras with the L-infinity algebras that are tangent to with the tangent L-infinity algebras to our simplicial Lie groups. So explaining these constructions is the task of this next section. In order to do this, I need to do a little bit of categorical, categorical background. So I'll introduce what is called the simplex category delta. It has objects, essentially the natural numbers, which we will identify with all of the natural numbers. So we'll identify n with all of the natural numbers less than or equal to n, and the morphisms are weakly monotone maps between them. We distinguish two special classes of these morphisms. First, we have for each n, n plus 1 distinguished inclusions delta I, defined as in this equation. And then second, we have n distinguished projections sigma. This is fairly technical, so it makes more sense if we use a graphic. The maps, so the inclusions delta I, they take the elements of n minus 1, and they just bump up I to I plus 1, and so there's a gap at I. On the other hand, the projections sigma I will collapse I and I plus 1 into I. It is even easier to see what's going on if we have with the second graphic. So here is my attempt to make this more tractable. These canonical inclusions delta I, they include n minus 1, indicated in red, into n as the ith face of this of these abstract simplices, or these abstract sort of looking simplicial complexes. So if we think of the natural numbers less than n as being the vertices of a simplex, then it sends the n minus 1 simplex into the face opposite I, the face opposite I. So this would be delta 0, this would be delta 1, delta 2, and delta 3. So then here's a diagram with the formal definitions on the left-hand side. So we have our canonical inclusions of non-degenerate faces. And on the right-hand side, we have sort of the heuristic picture. So these are including a generic face into the 0th, 1st, and 2nd slot in the next higher simplex. Okay, so now we can define what a simplicial object is. Given a category C, a simplicial object is simply a contravariant functor from the simplex category to C. We say that the n simplices of this simplicial object are given by the image of the natural number n under this functor. And then as a warning, if you're seeing this for the first time, just keep in mind that a simplicial object is not an object of C. It is essentially a diagram in C parameterized by or modeled on the simplex category. So the idea is that we have an object of vertices. So these are points, an object of edges, an object of 2 cells, 3 cells, etc. And the distinguished inclusions are then being sent to face maps. So inclusion maps become, because it's contravariant, then become face maps on the right-hand side in C. The distinguished projections are sent to degeneracy maps. So we have Greek to Latin delta. The face maps become, the inclusion maps become face maps, and the projection maps become degeneracy maps. Okay, so then we will just immediately specialize to the Lie group setting. And we can now define a simplicial Lie group to be a simplicial object in the category of Lie groups. So we have so it consists of a Lie group of points, a Lie group of edges, a Lie group of two cells, etc., together with the data of face maps between them and degeneracy maps going in the opposite direction. I will give two basic examples. First, we have the constant simplicial Lie group. So given any Lie group G, we can have all the Lie groups of simplices be equal to G, and every single structure map be the identity map. This is essentially the manifestation of the Lie group G as a simplicial Lie group, and I suppose it also exhibits the construction of simplicial Lie groups as an actual generalization of Lie groups. As a more interesting example, if we start with a strict Lie2 group, we can take the nerve, which is which is another example of a simplicial Lie group. So what I'll do briefly is to review the definition of a strict Lie2 group and then describe how the nerve construction is done. So a strict Lie2 group is essentially or informally, it's a category that instead of having a class of objects and a class of morphisms, it has a Lie group of objects and a Lie group of morphisms in such a way that all of the structure maps are Lie group homomorphisms. So from this, we can construct a simplicial Lie group where the points are original Lie group of objects. The edges are given by our Lie group of arrows. And then the two simplices are composable pairs of arrows. The three simplices are composable triples. And then in general, the n simplices are composable n tuples of morphisms. The ith face map, well, the zeroth face map is given by just deleting the first arrow. The nth face map is given by deleting the last arrow. And then the ith face map for intermediate I is given by composing the pair of arrows that meets at this ith vertex. And so this then uses the category structure of our original strict Lie2 group. And the ith degeneracy map is given by inserting a categorical unit at the ith vertex where these arrows meet. Okay, so now I will look at the infinitesimal side. Probably the most tractable characterization of an L-infinity algebra is as a graded vector space L together with a family of brackets. So this is in such a way that the nth bracket is graded skewed symmetric and is of degree n-2, and this whole family of brackets satisfies this collective Jacobi identity called the strong homotopy Jacobi identity. As a brief comment, this Jacobi type condition ensures that the underlying graded vector space together with the first bracket, so the L1 bracket, is a chain complex. And then if all of the brackets are 0 for n greater than or equal to 3, then our L-infinity algebra is called a strict L-infinity algebra, which are the ones that pertain to the simplicial Lie group setting. Okay, so I'll give two very basic examples of L-infinity algebras. First, if we're given any Lie algebra G, we can promote G to a graded vector space by putting G in degree 0 and setting the remaining graded components equal to 0, as shown in the diagram here. And then we can set the L2 bracket to the Lie bracket of G and have all the other brackets be 0. So this gives us an L infinity algebra. And as with the trivial simplicial Lie group example, this shows that L infinity algebras do generalize familiar Lie algebras. As a second, also kind of trivial example, given any positive chain complex, so this is just in the category of vector spaces, we can promote this to an L infinity algebra by setting the L1 bracket equal to the differential and all the other brackets 0. So such a L infinity algebra with, namely one with all the brackets besides the first one vanishing, is said to be abelian. All right, but of interest to us is the following. So we're starting with a simplicial Lie group. We take its by applying the Lie functor to the diagram, we obtain a simplicial Lie algebra. I'm going to describe in this slide how from that simplicial Lie algebra we obtain an L infinity algebra. So the underlying graded vector space is given by the kernel of all but the last face maps. So the kernel of di, or the intersection of the kernels of di for I strictly less than n. And then the differential is just that final face map. So the differential partial is here. As a comment, this construction from a simplicial vector space to a chain complex is one direction of the Dold-Kahn correspondence. Because we have more data, we have a simplicial Lie algebra. It can be shown that the Lie bracket structure on each of these levels determines a natural graded Lie bracket on the underlying graded vector space, and moreover that together with the differential this forms an L infinity algebra. And so this is what we will take to be the L infinity algebra tangent to our original, to our initial simplicial Lie group. In this very brief section, I will review the construction of the Chevalier-Eilenberg algebra of an L infinity algebra. And to do this, we'll first return to the Lie algebra setting and see how we can reformulate the construction in such a way that the generalization to L infinity algebras is immediate. So there are two observations. First, we note that the exterior algebra of the dual of our Lie algebra is isomorphic to the graded dual of the reduced symmetric co-algebra of the, I believe this is desuspension, not suspension, desuspension of the Lie algebra, thought of or conceptualized as a graded vector space concentrated in degree 0. So here I want the shifted Lie algebra to be in degree -1 for this section. Okay, so that will so this construction will apply immediately to an L infinity algebra. We can simply put an L infinity algebra in here for G. Second, we observe that the Lie bracket determines a degree 1 co-derivation or a co-differential on the space here of which we are taking the graded dual. So on the reduced symmetric coalgebra of the shifted Lie algebra. The Chevalier-Eilenberg differential can be characterized as simply the dual of that co-differential Q determined by the Lie bracket. So for an L-infinity algebra, we simply define the Chevalier-Eilenberg algebra to be the graded dual of the reduced symmetric coalgebra of the shifted underlying vector space with differential given by dualizing a co-differential Q on the reduced symmetric coalgebra of the shifted underlying vector space, which is uniquely determined by our family of higher and lower order brackets. So this is our differential. Okay, in this final section, I want to describe our my collaborators' claimed generalization of Cartan's observation to the simplicial Lie group setting. So as a reminder, our goal is to generalize this result, Cartan's theorem, to simplicial Lie groups. Well, the left-hand side of the generalization is clear. Here, with the classical Cartan result, with the classical Cartan theorem, we have the Chevalier-Eilenberg algebra of the Lie algebra of our Lie group G. Clearly, what we want here is the Chevalier-Eilenberg algebra of the Lie algebra tangent to an initial simplicial Lie group G circle. It remains then to determine what the higher manifestation of the left invariant de Rham complex will be. And it turns out, we claim, that this will be a quotient of the totalization of the left invariant normalized Bott-Schulman-Stasheff double complex. So what I'll do in the remainder of this talk is to explain what this is. And I'll start with the Bott-Schulman double complex. It is essentially the de Rham complex on a simplicial manifold. Actually, this is more general than a simplicial Lie group. So it is a double complex where one of the gradings describes the form degree, and the other grading describes the simplicial degree. So the whether we're talking about the space of points, edges, two cells, or Q cells, as indicated here. It comes with two natural differentials, the de Rham differential, which increases the form degree by 1, and a simplicial differential, which increases the simplicial degree by 1, and which is defined as an alternating sum of pullbacks by face maps. So the normalized Bott-Schulman-Stasheff double complex is given by restricting to those forms alpha which vanish along the degenerate subspaces. That is, the pullbacks by any degeneracy map of which is 0. Which satisfy the condition that if they the condition that every degeneracy map pulls them back to 0. So far, that gives us a differential and an underlying graded vector space, but we still need a product. So it turns out that there is an associative product, which we'll denote by cup here, which happens to be compatible with all of the gradings and the differentials on the Bott-Schulman-Stasheff double complex, and which restricts to the normalized double subcomplex. It's given in the following way. If we have, so I'll refer to the picture at the bottom, which is maybe more clear than the equations. If we start with a form alpha on GQ and a form alpha prime on GQ, I'm sorry, and a form beta on GQ prime, then we'll pull, then the cup is going to be a form on GQ plus Q prime, which is given by pulling back alpha by the front along this front face and pulling back beta along the map that that returns the back face, and then wedging them. So this, as mentioned, this is compatible with all of the underlying structures. I see I have 2 minutes. This is the final slide. So we might then think, or we might ask, well, is the sought after higher left invariant de Rham algebra then the totalization of the G invariant normalized Bot-Schulman-Stashev complex together with the product given by with the multiplication given by this cup product and the total differential? Well, it turns out that no, it's not. There are two complications. First, the cup product is non-commutative. So this construction isn't even the kind of thing that our Chevalier-Eilenberg algebra could be isomorphic to. And then second, it also turns out that this space is too large. That is, there are elements here that do not correspond to duals of elements in the reduced symmetric coalgebra of the normalized chain complex of the left invariant vector fields shifted by 1. So what we are currently in the process of writing up, and so validating all of the details, of which there are many, is that if we take instead the subspace of this algebra generated by the 1 forms and then quotient out by forms that annihilate the a certain space of left invariant vector fields and multi-vector fields on the underlying simplicial Lie group, then we do have an isomorphism on the nose, and then that would be the differential geometric construction to which the Chevalier-Eilenberg algebra is canonically isomorphic to. So thank you very much.